This integral involves cube roots, fourth roots, and a logarithmic term. While it appears complex, we can simplify the entire expression by using a substitution that eliminates all fractional powers.
Identify the indices 3, 4, 6, and 2. These values determine the substitution required to simplify the radicals.
12 is the least common multiple of these indices. This value allows us to define a substitution that will transform the variables into a polynomial form.
We substitute x with u to the power of 12. This transformation converts every radical term into an integer power.
The expression now consists of integer powers of u and a logarithmic term. We can now proceed with the evaluation.
To simplify the calculation, we will split the integral into two parts, I1 and I2. We will evaluate each term separately.
We will evaluate the rational part first, followed by the logarithmic part. Let's begin with I1. The first part of the integral, I1, is a rational function. We can simplify this expression by factoring the denominator and reducing the fraction. First, we factor out the coefficient of 12. Then we factor the denominator to prepare for simplification. Simplify the powers of u. The degree of the numerator is 8, while the denominator is 1. Since the numerator degree is higher, we apply polynomial division. Instead of standard long division, we can use a substitution trick by adding and subtracting 1 in the numerator. This method is often more efficient for these types of expressions. This technique separates the fraction into a polynomial with alternating signs and a remaining term that is easily integrable. We apply the power rule to the polynomial terms. The remaining term integrates to a natural logarithmic function. Distributing the 12 completes the evaluation of the first part, I1. With I1 completed, we will now proceed to evaluate the second part of the integral, I2. The second part of the integral involving the logarithmic term appears complex. We can simplify it using a series of algebraic transformations. First, we factor out u to the fourth from the denominator to simplify the rational portion of the integrand. The term 1 plus u squared appears in both the denominator and inside the logarithm. This common term indicates our next substitution variable.
We use one factor of u for the differential. This leaves u to the sixth, which we can express in terms of t as t minus 1 cubed.
Substituting these terms into the integral transforms the expression into a form involving only the variable t. We expand the cubic term and divide each part by t. This results in 4 separate terms that can be integrated individually. To evaluate these terms, we will apply the method of integration by parts in the next step. This expression involves products of polynomials and a logarithmic function. We will apply the method of integration by parts to evaluate each term. Utilizing these general integration formulas will simplify the calculation process for each individual term in the integrand. We integrate each term separately. Each polynomial term times the logarithm results in a combination of logarithmic and polynomial terms. We now combine the individual results. By grouping the logarithmic terms and simplifying the coefficients, we obtain a single expression for I2. The final step for this part is to reverse the substitution by replacing t with 1 plus u squared. This results in an expression in terms of u. We have completed the evaluation of both components. We will now combine I1 and I2 to reach the final solution. We have evaluated both components of the integral, I1 and I2. We will now combine these results to form the complete solution. Combining all individual terms results in a single expression in terms of the variable u. Each previously evaluated component is included in the summary. To reach the final answer, we must express the result in terms of the original variable x. We reverse the initial substitution, x equals u to the power of 12.
Substituting u for x to the power of 1/12 gives the final solution. The initial complex integral has been evaluated through a systematic series of substitutions and integrations.